Okay, so just picking off where we were yesterday, because I didn't record everything, but just to remember that the anode is where oxidation occurs. You can remember the mnemonic and ox, or you can remember that these both begin with vowels. Similarly, the cathode is where reduction occurs. You can remember red cat, or you can remember they both begin with consonants. So it's up to you. But the electrons always flow from anode to cathode. Doesn't matter what kind of electrochemical cell you have, you're losing electrons here and you are gaining electrons over here. Now, here's another thing. Over here on the anode, you are changing metal into aluminum, or you're changing a metal into a metal ion. So you are going to actually create a solution that's more positive over time if you do not counteract that increase in positive charge by importing anions. So you have this salt bridge over here, and one of the functions is to balance out the charge so you don't build up a resistance and your electrochemical cell comes screaming to a halt. So you have your anions, and they're going to actually come over into your anode or towards your anode to balance out charge. Right? Because what's happening over time is that this solution is becoming more positive, and to balance that out you have to have your anions, which are negative, and then you keep the charge neutral of that solution. Similarly, over here in the cathode, you're turning your copper ion, that was probably from copper nitrate or some neutral solution, into copper metal. So you are taking positive ions out of solution, and this solution, if you didn't have a salt bridge, would become negative. So what you have to do is you have to import cations from the salt bridge towards your cathode. So anions go to the anode, cations go to the cathode. Okay? Now, the other thing is we want to actually take this cell and then figure out how much energy or work we can get out of it. So one of the important things to look at is something called a reduction potential table. So what you see is there's a table, and it's called reduction potential table because everything's written as a reduction. And you see these voltages that are associated with these reactions. There is a standard hydrogen electrode which is set up as our 0 point. And basically what a volt is, which is also sometimes called a potential or an electromotive force, is this unit. It's joules per coulomb. Now, joule is a unit of energy. Coulomb is a unit of charge. So really what it's telling you is the amount of energy that you will get or that you have to put in to move this charge, okay, to move the charge. So just to give you some context, one electron, when we say it has a -1 charge, it actually has a charge of 1.6 times 10 to the -19 coulombs. I rounded there. So a mole of electrons, all right, which is, right, multiplying this by Avogadro's number, will give you roughly 96,485 coulombs of charge, which is also called a Faraday. So every time we move these electrons or move these charges, there's a certain amount of work accomplished, all right, or a certain amount of energy that's transferred. If you have a positive voltage, then you are getting energy when you transfer that charge. If you have a negative voltage, you're putting energy in. Now, the important thing is this is a ratio. So it's the amount of energy you get for every coulomb of charge. And every reaction has a different voltage because the amount of energy you get or that you put in is related to the stability of the substances you're dealing with. But this ratio still holds true. It doesn't matter how many times I do this reaction. So I'm just going to write that voltage stays the same even if I do a reaction gazillion times, okay? And the reason for that is it's the energy per coulomb, just like the price per movie ticket. If you go to the movies, it's $10 for a ticket. If you go 5 times, it's still $10 per ticket. You're obviously going to get more energy if you do more of the reactions, but the energy per coulomb moved is still going to be a set ratio, just like the cost per movie ticket is going to be the same price no matter how many times you go. Okay? So now, Recall, these are all written as reductions. So when we have an electrochemical cell, we have both reductions and oxidations. So when we go and try to calculate the electromotive force or the cell potential, what we have to do is we have to add the reduction potential for the reduction happening at the cathode, and we have to add the oxidation potential for the reaction happening at the anode. Now obviously if you have a table where everything is written as a reduction, to have it become an oxidation, I have to flip the reaction, and when I flip the reaction, what happens is the sign of the voltage changes. So just take the negative of the opposite half reaction. So for example, if you take a look at this reaction, I would look for the reduction potential of this, and I'd look for the reduction potential of this. And because I'm doing the opposite of this reaction, I would flip this and change the sign of the voltage that I get, which I don't know off the top of my head. And then I'd have to add those up. It does not matter that I am doing this 2 times or 3 times. Do not multiply the voltage, because remember, it's the energy per coulomb of charge. All right, that's a trick question they love to ask. The other thing to mention here is that what you are calculating is your standard state cell voltage. So this is when all the concentrations are at 1 molar. Now obviously as your reaction starts to happen, your cell potential is going to stop, is going to decrease until it gets to 0, right? This is when your battery is dead. And this is actually the equation for it. You don't have to memorize it. But the idea here is that your reaction is going to go towards equilibrium, right? KEQ is when the cell potential is 0. So you should know that equilibrium governs this particular reaction too. If I increase the amount of my aqueous substances, I can actually make the reaction push forward more. So that will give me actually a more positive cell potential, give me more energy for every coulomb of charge that I transfer. If I decrease the amount of product, all right, some batteries are designed to actually pull out the ions that you are creating by precipitating them out, all right, you're also going to push this reaction forward. So it's going to respond just like you would expect to equilibria, just like Le Chatelier's principle, all right? Just remember, the cell potential drops as the reaction proceeds until you get to 0, which is when a battery would be dead or when you would have reached equilibrium, okay? Just in terms of some other terms, if you have a positive voltage, then your reaction is spontaneously happening. Those electrons are transferring, and that means that your delta G is negative, and it's called a galvanic or a voltaic cell, all right? So this is a good example of that is a battery, and this equation kind of connects the delta G with the cell voltage. My cell voltage should be positive, negative times a positive makes me have a negative delta G. And just to tell you what these terms are, N is the number of moles of electrons transferred, Faraday is the coulombs for every 1 mole of electrons, and the voltage is the joules for every coulomb of charge. So you'll see that all the units cancel out until you're basically left with the free energy change, which, remember, is what happens to the amount of available work, right? And if you decrease the amount of available work, then it's going to happen. If you have a negative voltage, on the other hand, okay, you have an electrolytic cell. So this is not something that happens spontaneously. You would have to put in some energy. So that's like charging a battery. Your battery in your phone does not spontaneously charge itself. You have to plug it into an outlet. Or electroplating, if I put energy in to plate it with some kind of metal I want. The key thing here is that the delta G is positive and the E is negative. And you can see if I have a negative cell voltage, because of this equation having a negative here, my change in free energy is going to be a positive number. All right. In terms of some other things you might see this kind of shorthand, and all it is saying is that here's the reaction that's happening in the anode. Anode always precedes cathode. This little double line represents the salt bridge, and then here's the reaction happening in the cathode. Pretty straightforward. Okay. just quickly in terms of balancing, I think the rules that you want to apply, which I'll write down really quickly, is 1, you want to balance any substances beside hydrogen and oxygen. All right. Then you want to balance oxygens by adding water, which obviously has oxygen in it, but also hydrogen. Then you want to balance hydrogens by adding H+. Then you want to balance charges by adding electrons. And then you want to multiply your half reactions. So the number of electrons lost equals the number of electrons gained. And then you can combine your reactions and simplify. All right, so combine, simplify. This is for an acidic reaction. So if you want to turn it into basic, right, you're going to want to neutralize your H+ with an equal number of OH on both sides. All right, so going back to that example, so I'm running short on time. If we take a look here, I have the first step. I wanted to balance out my chromiums here and my carbons here, so I added a coefficient of 2 on the right of both reactions. Then I had 7 oxygens here, but none on the right side, so I added 7 waters. The oxygens are balanced over here on this reaction over here. Because I added 7 waters, I actually have 7 times water, so I have 14 H's. I have to add 14 H's here. And then if you look at the total charge, I have positive 12 on the left of this arrow, positive 6 over here, so I have to add 6 electrons to balance that out. Over here, I have, what is it, negative 2 and 0, so I have to add 2 electrons on the right side. I have 6 electrons that I am gaining here. I have 2 electrons that I'm losing, so I have to multiply the right reaction by 3 to make the number of electrons the same. I add everything up, and what I get is this final reaction here, written in black, if I want it balanced for acidic solutions. If I want a basic solution, I have to neutralize my hydrogen ion by adding an equal number of hydroxide to both sides. And what happens is the hydrogen and the hydroxide turn into waters. And if I simplify that, because I have water over here and I have water over here, you will actually get the following reaction for basic reactions. Okay? So you would probably want to practice that, but it's a time-consuming problem, so you don't want to do the balancing of redox reactions as the only thing if you have not that much time. And just so you know, the number of electrons lost or gained is going to basically back up what you know about